So let's go ahead and do some examples. So in these two examples, what we're going to do is find angular speed and linear velocity. So we'll look at some strategies for each. So again, on this first one, what do we know about angular velocity? Well, we know that it's the angle that I swept out divided by time. Right? What do we know about linear velocity? Well, it's the distance that I travel over time. And then we also know that these two can be related if needed, right? Oops. V equals R omega. All right, and so let's see if we need these or if we can use some other strategies coming forward. So in the first one, right, for the angular speed, right, they're asking us to find the angular speed for a tire rotating at 5 revolutions per second. Okay, so again, if you take a look at our formula for it, right, we need an angle theta, but they didn't really give us an angle theta. But they told us some very important information, right? They told us that we're basically rotating 5 revolutions. So to find our theta, right, we know that every rotation is 2 pi radians, and I went through 5 rotations. So the angle that I'm sweeping out is 10 pi radians. All right, so there's my theta. How much time did I do that? Well, I'm doing that every 1 second. So my omega in this case would be 10 pi divided by 1, which gives us 10 pi radians per second. All right, so there would be our angular velocity for that. So before we could actually use that nice handy-dandy formula, right, I had to kind of think about what it meant, all right, to get an angle when given revolutions. That's going to be kind of a common theme here. So the second hand of a clock, right? Again, how fast is that rotating as we watch it tick, 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 tick through the clock? Well, again, I want to use this formula up here, right? And I know we're dealing with a second hand, all right? So we got to figure out, right, how many, what's my unit time and how far did I rotate? Well, for a clock, right, as we go through a clock, we know that that second hand, tick, 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 goes through a full revolution, so 2 pi, right, in 60 seconds. All right, that is what a second hand does in a clock. So it goes a full rotation, 2 pi, in 60 seconds. So we got everything we need. So my omega, being theta over t, is 2 pi over 60, and doing a reduction, we get pi over 3, and this would be radians per second. So that would be the answer for letter B. Letter C, we have a disk that's doing a half turn in 0.12 seconds. All right, so kind of in line with what we've been doing, right? I'm going to rewrite this 12 seconds, right? This is 12 over 100, which it could further be reduced to 6 over 50. So we're basically going 6 over 50 seconds. There's your time. Now we got to figure out our theta. Well, we're told we're doing a half turn. So a full turn is 2 pi, right? So half of that turn gives us pi. So there's our angle that we're rotating. Here's how fast I'm rotating it per unit time. So we're ready, right? So what's omega? Well, it's by definition theta over t. My theta is pi. My time is 6 over 50. So we're dividing by a fraction. So that means I'm actually multiplying by a reciprocal. And so it looks like our omega in this guy is 50 pi over 6. And again, there's this exact value. You can obviously turn to your calculator to get an estimate. But that's pretty quick, right? And this is, again, radians per second, since that's our unit time. Okay, so there's our round of finding angular velocity for some given situations. All right, so how about, I'm already almost 5 minutes into this, so how about I stop this video and we'll come back and we'll do the second portion, the linear speed, in another video coming soon. See you in a moment.